to our second special DITP Ehrenfest Colloquium. As you know, this is every now and then we have a really special person coming to talk to all of us, sponsored by the Delta Institute of Theoretical Physics with Amsterdam and Utrecht. And today, for me, it's great to be able to introduce to you Paul Townsend, who is great because he was my thesis supervisor, so it's very personal. I was your first PhD student, I think.
I think so.
So Paul is one of the great names in supergravity, supersymmetry, superstrings. And I've had when Vincenzo asked me to introduce him, I had the difficulty of summarizing him for you in a few sentences. It's really hard. For many years, when we were together working in Cambridge, we would be having a conversation about you name it, and after half an hour he would say, I wrote a paper about this, and then, of course, he would have written an absolutely seminal paper about whatever it is that he was discussing. And this was my experience. I had the impression that he had worked on absolutely everything. It's not far from the truth, if you think of it. But if I have to select like 3 themes, perhaps the study of solitons in supergravity is one of the things that stands out, and not because they were solitons, but because you can ask the question, if you imagine having a supergravity theory and you put in a domain wall in there, because the domain wall is made out of scalar fields, the scalar fields give mass to the fermion fields, and the fermion fields are happy on the brain, so to speak, on the memory. And so you can ask questions about the low energy theory. So if I make this now infinitely small, so infinitely thin, it becomes a 2-dimensional surface. And the main question you want to answer is whether from the point of view of this low energy excitation theory, the membrane, the theory as seen from the membrane, whether this has also supersymmetry or not. And it turns out that there's a very specific set of dimensions, and dimensions for the defect and dimensions for the ambient spacetime, where you can have this sort of double supersymmetry. You can have, okay. And then the first major thing that they did in this was to find out that you could have super membranes in 11 dimensions, which was, the highest dimension in which you can have supergravity. This was huge. At the time, the superstring in 10 dimensions was known, but that was it. It was supposed to be perfectly special. And then Paul and Erik Bergsoe and Erwin Setzgen showed that, in fact, supermembranes also were very special in this property. And after that, there were more cases that were known. Paul being Paul, he has an absolutely wicked sense of humor. So, what do you call these defect type things, or these surfaces embedded in other spaces? Well, a membrane is a 2-dimensional brane. So you can talk about 2 brane, a 3 brane, whatever brane, and then this became, for a p-dimensional object, a p-brane. And so then there was all these jokes about the brain scan and the p-brane, and so he invented the term p-branes. So actually this is now in the Oxford Dictionary, and somebody else took credit for it, but it was your idea.
Oh well.
I can say it here.
I don't think many people read the Oxford Dictionary, do they?
He coined the term brain. It's not a good thing. But so there was this business of dualities in string theory, which is also connected to all this, whether they are defects or. And then the third theme, besides these super membranes and these soliton things, is 2 + 1 dimensional gravity, which is something that he did many years ago. By some fantastic work there, and now he has retaken this with Erik Bergsoe again and a bunch of other people, and now they're finding massive versions of gravity in this 2 + 1 dimensional world. So I could go on for the rest of the hour, so if it's...
Leave me some time, Anna. Leave me some time.
So let me just say quickly that you had your PhD in Brandeis University, had a bunch of very prestigious postdocs in Stony Brook, which was one of the meccas of supergravity then. You were a CERN fellow, and you were at the École Normale also with the Joliot-Curie fellowship. And luckily for me, in 1984, he took a position in Cambridge just about when I was arriving. So the rest I've already told you. And I leave you with a fantastic lecture.
Thanks very much, Anna. Of course, you played a big role in the three-dimensional gravity too, as I recall. One of the, actually, of course, not before I met Anna, because I think actually we met in Spain. It would have been, in fact, around then, actually, 83. I'm going back to, so the title of my talk, Let's Twist Again, is, well, it's just that I like titles, as I was saying, that you can sing. So perhaps the subtitle explains it better. And that's what I want to tell you about today, is it's a relationship between these three things. Division algebras, a topic in basically 19th century mathematics. Twistors, Penrose's idea, and supersymmetry. And so they're all, those three topics are actually closely interrelated. And so that's what I want to try to explain this evening, what the interrelation between them is. Now, I'm going back here, so to you see, past as a theme that I was interested in long ago in 1983. In 1983, I actually visited Japan and China. And, well, I won't recount, I could count various things there, how we got into this whole thing, but it was because there was this Japanese dictionary of mathematics. It was all in Japanese. It was pre-internet. If you wanted to find out mathematical facts, it was the easiest place to find them at that point was in this Japanese dictionary of mathematics, which is all in Japanese. So you have to understand Japanese. Unfortunately, Taichiro Kogo did understand Japanese. And so we got out this dictionary, and it had all kinds of tables. And that's looking through all these tables, we realized that there was some kind of connection between division algebras and supersymmetry. So that was the thing in 83. That was the work. So we didn't really do very much, actually. We kind of took some empirical ideas, then looked at all these tables and sort of proposed a general kind of scheme for how things were going to work. Sudbury picked up on that and made some important contributions. He kind of extended it in a way I'll explain, or rather won't explain, but at least comment on. Twistors didn't get into it at that point. There was actually a paper in 83, important one that is relevant to what I'm going to tell you about, in fact, by Shirafuji. Funnily enough, he wasn't in Japan, he was visiting Oxford at that time. And so visiting Oxford, I guess he got interested in twistors. He wrote this paper. But that fed into, I didn't really even know about that until much later, but that fed into work that Bengtsson and Cedarwall did later, the connecting division algebras and supersymmetry with twistors. So at that point, there was a kind of connection between these three ideas. And it was all mostly in the context of first of all, in the context of particle mechanics. And that's one of the reasons, in fact, the mechanics of a free particle. Now, there isn't much simpler than a free particle, one free particle. So that was one of the motivations for me choosing this particular topic tonight, because if you look at it, you might think twistors, oh dear. You open a book on twistor theory and you're immediately into sheaf cohomology. That, I think, would not have gone down very well. But you can, don't worry about that, because twistors actually will be the output here, not the input. So you don't actually have to know anything at all about twistors. I'm going to tell you in a moment about just division algebras. I'm sure many of you will have heard that story before. I'm going to skip a lot of things about, I'll just sort of mention some facts, I think, about supersymmetry, because realistically I won't have time to do anything more than that. And let me just mention the again in the title here. I got interested in this again this summer because of various developments. That this was all in the context, as I say, particle mechanics down here, and indeed massless particle mechanics. And that's natural if you think about twistors, because if you know anything at all about twistors, you'll probably think, well, it's to do with solving massless wave equations. That was the original thing that Penrose was interested in. It was a way of trying to write down solutions of massless wave equations. Although he kind of erected a very complicated philosophy associated with that, which is in fact relevant to what I'm be saying in a moment. But in fact, you can extend that to the case mass not equal to 0, and that's part of the interest. And recently, but I will not really be able to say anything about that. I'll just sort of mention at the end why it's relevant. That's about as far as I'll be able to get, I think. So let me begin by first of all saying division algebras. Let's start with that one. So let's see, now there's probably a preferred order in which to use these blackboards, green boards, but let's see if I can be systematic about it. So, division algebras. Well, let's just take the complex numbers. So, complex numbers you can just view as a pair of real numbers. So it's really a vector in a two-dimensional vector. So in a vector R2 vector space. But of course there's a multiplication rule. Multiplication rule, which of course, as you know, is equivalent to I squared equals -1, where z is equal to a plus ib. So you can summarize the multiplication rule in that way, but you could write it without involving I, just as a multiplication rule of ab times cd. And so you multiply two of these things together, two of those complex numbers, you get another one, and that turns it into an algebra. So that this turns R2 into an algebra. Let's just call it C. And then what are the properties? Well, there are a lot of properties, but the ones that are going to be important for what I'm going to say now, they include two properties here. Well, the first one is that if you take z1 times z2 is equal to 0, then this is equivalent to saying that z1 is equal, either z1 is equal to 0, either this, or z2 is equal to 0. So that's property 1. And if you think about that, what that means is that allows you to divide. That effectively tells you that any number can have an inverse, because, for example, given except 0. So if you've given z1 not equal to 0, and you have z1, z2 is equal to z3, which is then given, then you see, if it weren't true, I've said that z1 is not equal to 0. I mean, if there were a z2 not equal to 0 now, you could just add it. So if there was some z2 not equal to 0 for which this was still true, then it's clear that you could just add that in here, and that simply wouldn't affect this equation. So you wouldn't have a unique inverse. So the effect of that is equivalent to saying that this is essentially equivalent to the statement that z not equal to 0 has a unique inverse. So you can divide by it. And so this is the property that makes it a division algebra. So that property makes C is a division algebra. Now, my title, I said a division algebras, but strictly speaking, the theorem that I want to quote to you in a moment is also requires property 2, which is that each z in C has a positive norm, which is just the modulus. So that, in fact, for complex numbers, that is equal to the square root of z bar. So the idea is you can take the conjugate by taking the imaginary units, changing the sign, and then that gives you this modulus, and that can be viewed as a positive norm. And the point is, in order to qualify as a norm there, it should have the property such that Z1, if you take the norm of Z1, Z2, you should get the product of norms. And of course that is true for the modulus of complex numbers when you multiply them. And so that's property 2, and these two properties mean that C is a normed division algebra. Now, basically, it was in fact Hamilton who first introduced the idea that you should really think of complex numbers just as a pair of numbers. Prior to him, Argand and various people had pointed out the fact that you could the complex planes. The idea of a complex plane was already known, but the slightly more abstract point of view that it was just a pair of numbers was the point of view that he was taking. And he had the idea that he wanted to generalize it to 3 dimensions. And what he was actually trying to do was, in fact, to generalize these two properties. So he wanted to have an inverse. He wanted to be able to divide by. He wanted to use some new kind of number. He wanted to be able to divide by them, but he also wanted to have this basic property. And of course, he found that he wasn't able to do that. And if you, for example, if you think in 3 dimensions, if you take vectors in R3, if you take the cross product, then of course it's not true that the cross product of 3 vectors, if that's equal to 0, doesn't mean that the 3 vectors, one of the 3 vectors has to be 0. They could just be orthogonal. And if, on the other hand, you take the dot product, then you could get 0 just by taking them to be, sorry, if it's the dot product, you just take them to be orthogonal. If it's the cross product, you just take them to be parallel. So he couldn't succeed, but he discovered that you could do it if you went to 4 dimensions. So so if I can move that up, yep. So Hamilton tried the same for R3 and failed. But then he succeeded for R4. My handwriting not very good, I'm afraid. So in a flash of inspiration, he realized that he needed to go one higher dimension for R4. And then basically what he did was invent a multiplication rule, which then turns R4 into an algebra, which in fact is the algebra of quaternions, which we call H after Hamilton. You can't really call it Q because that would be the rational numbers. And in fact, there was a guy who did it before Hamilton, who was called Rodriguez, but you can't call it R because that would be the real numbers. So, by fortunately for Hamilton, but it was independent work. But the guy nobody took any notice of what Rodriguez did. But the moment that Hamilton did it, he sent some notes to his friend from college, a guy called Graves. I should say, first of all, before going into that, of course, the point here is that you just introduce the multiplication. You just introduce, so Q is in H, and you say Q is equal to A plus IB plus JC plus KD, and then you have the multiplication rule for quaternions. I squared is J squared is equal to K squared is equal to ijk is equal to -1. And so that, although I haven't seen it, is supposedly inscribed on the bridge somewhere in Dublin. And if you can play around with that, and you can soon convince yourself that this implies, in fact, that ij is equal to -ji, and therefore it's they're non-commutative. So he was very excited. He sent this off to his friend, a guy called Graves. And Graves immediately wrote back saying, I've generalized it further. And what Graves had found was that you could do it for R8. So Graves said that, found a multiplication rule such that R8 could be viewed as a division, a normed division algebra, which in fact we now call the octonions. And again, you can summarize all of the rules that basically this, by having by these rules I, j, and k, essentially you can see fairly quickly you can divide by any number other than 0, and that there's a norm constructed in the usual way. The norm is just the same as here. You just have a conjugation, number times its conjugate, then take the square root, and the conjugate means you just change the sign of all of the imaginary units. And so what he found was that you could do that for R8. And the rule for multiplication is this so-called Fano plane, in which you have 7. So the multiplication rule can basically be summarized by this. You have seven lines, and you have 7 points. 7 lines and 7 points. Here I'm drawing in some lines for you. So that's 1, 2, 3, 4, 5, 6. That's 6 lines. And at the moment we have 7 points there now. These down here, that'll be an I, that's a J, and that's K from the quaternions. And then the other line, I only have white chalk, right? So, oh no, well.
Well, tradition at Colloquium Ehrenfestii, one should use exclusive.
Okay, I'm not going to break tradition. I'm not going to break tradition. No. Because I realized actually why I was asking for the other chalk, that I didn't want it, because I don't want to make a distinction. The point is the other line here. The other line here is you draw a circle. You circle like that. That's a line. I mean, all of these things. Actually, these lines, I should really do them. You know, they should be done like this, because you can think of all of these lines as going off to. You can think of them all as going off to infinity and sort of joined up at the end. So they're really all circles, actually. Because this is lines. It's really projective geometry. So. And so that's the 7th. So this circle is the 7th line, and then the point is that if you there's some arrows on this to tell you some signs, but the point is that if you take this one times this one, you get that. You just continue on the line. So if you take so for example, this times that will be that one, whatever that imaginary. So the 7 points are the 7 points are the imaginary units, right? They're the imaginary units. And this tells you if you multiply one by another one, you get the third one on the line. So if you multiply this by this, you come around here and you get this one. And so you can also see that each point is on 3 lines, and each line intersects 3 points. So it's a very kind of symmetric kind of diagram. While I was just writing this, I was remembering that there was this song that my parents used to sing. It was called Seven Brides for Seven Brothers, I think it was. 7 Brides for 7 Brothers. It's a musical. It's an old musical, 7 Brides for 7 Brothers. But as far as I recall, in that musical, each brother had only 1 bride. But in this one, you see, each brother has 3 brides. So, and it's all 7, so 14 people. You divide them into brothers and brides, and each of them has 3, each one has 3 of the others. So I think it's a metaphor for a kind of harmonious, polygamous society of 14 people. That's how I see that. Because it's completely symmetric and nobody can complain. That's the idea. And that's kind of, I think that's Rawls' principle of justice or something. Anyway, there's kind of whole philosophy you could develop around that, I think. But that's the that's the Fano plane. I had to put that in just to, but I'm not going to really use that. But it's an useful kind of interesting to know. It's one of those facts that you'll never use again, probably. But what happened, of course. Now the point about the octonions is that, and actually, when Hamilton got this letter, he worked it out. He realized that these multiplication rule. The point is that for the octonions, you have you can define thing associator. So that's ABC minus ABC, and the point is that that's not equal to 0 for all ABC in the octonions, and so this is non-associative in this case. And in fact, these terms, non-commutative, non-associative, actually, it's from this kind that they derive. I mean, this non-associative, the word non-associative, or the word associative, of course, was only invented when came along something that wasn't associative. That's the, and then of course, it was invented precisely in order to describe the situation in the octonions. So that's in fact the origin of the ideas about all of these things in algebra. At any rate, the point is, and now we come to the punchline, is that so you've got so far, and then nobody else managed to find any others. There is a process, you can get some kind of number systems, but if you're going to demand to have these 2 properties, you want a norm division algebra, then in fact you don't get anything else. And so there's a theorem of that, which was proved in the late 1920s, I think, which is by Hurwitz, the mathematician Hurwitz. And he says essentially there are only 4 normed division algebras over the reals. So, and they are, and I'll give it some generic name K. So you have R, C, H, or O. So you have just 4 of them. Now, the next thing I want to explain is there's a connection, direct connection to relativity. So this is directly related to relativity in the following way. So you see, and so by relativity now I'm going to mean relativity in some space-time dimension of dimension d. So I should say here for space-time dimension is equal to 2 plus the dimension of whichever that one is there, and of course let me add here. Of course, the dimension of those is equal to 1 for that, 2, 4, and 8. So, for this dimension, which is of course equal to 3, 4, 6, and 10, if you just substitute in these numbers, you see you can represent a Lorentz vector by a 2 by 2 Hermitian matrix over K. So, for example, let's supposing we just look at some. So, in other words, the statement is this: that take xm, just the coordinates, not really a vector, but if we're in Minkowski space, it's good enough. So, I can represent that by some 2 by 2 matrix, which is x plus x, x bar, x minus. Breaking a lot of chalk here. X plus or minus is equal to x0 plus or minus x1. Say it's just 2 real numbers, but call them this. So those are reals. And then, of course, x here is going to be in K, this number system, which are either the reals, complex, quaternions, or octonions. And you see here the number is you have 2 plus the dimension of the space. So that's this 2 plus dimension K, 3, 4, 6, and 10. Now, the point about that, why is that? I mean, so why am I saying that why would I think want to write a Lorentz vector in this particular way? Well, the point is, take the determinant. You can see here that if you do take the determinant, well, I've already run out of board space. That's terrible. I'm very inefficient about using these boards. If you take the determinant there, so if you take the determinant, well, generally speaking, you have to be a bit careful about how you define the determinant over when you've got non-commutative numbers, etc. But at least for this particular case, it's rather easy to see what happens, because it's just x plus times x minus. And if I've given you this, then you see that you get x0 squared minus x1 squared, and then you get minus xx bar. But that's, as I told you before, the way that you get the norm is just by multiplying a number by its conjugate. Then you would take the square root to get the norm. In other words, you have the norm squared here. So minus x norm squared. But in fact, it should be clear, of course, in the case of a complex numbers, what this is just the norm squared is just a squared plus b squared. And of course, exactly the same would apply in the quaternions. It's just a squared plus b squared plus c squared plus d squared. It's the usual norm standard metric on Rn, R8, or R whatever it is. So in fact, this of course is just the Euclidean Euclidean length of x as a vector in R 1, 2, 4, 8. So this is equal to just it's equal to xm in my, I'll write it like that to begin with. So in my metric convention, where it starts out with a minus plus plus plus, it would be minus that, and that's simply equal to minus x squared. And the point is, it's Lorentz invariant. So this is Lorentz invariant because it's just the what's it called? Not the length, the interval squared. But of course, it's also easier to see that you get a Lorentz invariant quantity. The determinant is invariant by simply conjugation. By supposing I take a linear transformation on x, conjugate x. So but we also have is also invariant under x goes to L dagger x L, provided we have det of L dagger is equal to 1. And here here is just some 2 by 2 matrix. It's 2 by 2 matrix over whatever system, whatever division algebra we have. So you see the number of independent components of this 2 by 2 matrix is just, well, you got 4 entries. It's 4 times whatever that is, 1, 2, 4, and 8. And then you simply subtract the 1 for the determinant. There's a slightly special situation in the context of the... So this simply defines, let me just say this defines SL2 Okay. Not quite for 4 dimensions. In the case of the complex numbers, there are really 2 separate definitions of what the special linear group is, because the point is the determinant can be defined in 2 ways. You can take the complex determinant, or you can take the modulus of that determinant, which is real. So this would correspond to taking the real one, but it's a difference of 1. I'll just ignore that difference for the moment here. Yeah.
So now you have, over there the things on the diagonal were real numbers.
Yeah, that's right.
But now they're not.
No, because this is supposed to be Hermitian, but I'm taking the Hermitian. I'm just conjugating this Hermitian. This is still Hermitian, right? Yeah, that's right. Yes, yeah. Because you take the Hermitian conjugate, right? You get back to the same thing. So it's consistent with the hermiticity. Yeah, that's right. Yeah.
I'm asking whether so in L we don't require that
No, I just look for some general what's the general transformation preserving the hermiticity, and this is I said the only relation you require for the determinant is you need basically this relation on the determinant of L. You need this.
That means that that the L0 or the L plus and the L minus can be any element of.
Well, yeah, this is this is not Hermitian matrix. That's not representing a vector, right? It's Lorentz transformation, in fact. That's what it is. It's because I haven't proved it. What I'm telling you here is just that clearly this is Lorentz invariant, and I'm considering the most general transformation I can think of, and that defines this group here. And then you can just check the dimensions of those things. There's a check that's the same thing. As I say, there's a slight subtlety you have to worry about in the case of real numbers because there's definition of determinant. But let me pass over that. Yeah, I'm just looking for the border rubber. Oh, yes, here we are. Got it here. It's on the floor. Oh, no, I've got it. Yeah. The same way, this quantity, well, maybe I should have put it in a different color or something, but this is right, this x is you write it out, it has, right, there are 4 numbers in there. Or, well, 1, 2, 4, 8 numbers in there.
Okay,
right?
so if I have 4 numbers, then
it's they're separate. There are 4. Well, let's take the case of. There are dimension k of these, and then there are 2 of those. So I say you start with the dimension of space-time, which is 2.
also true for the L's. That is the question.
No. The L's it's just some 2 by 2 matrix, which you preserve. I write down the most general thing I can think of that has the, and of course.
So complex numbers there is x0 and x1. I can understand that. So there are 2 components.
Now for complex numbers, you have x plus x minus, and then x is x1 plus ix2. And this then is x1 minus ix2. So you have x plus x minus, well, sorry, not x1, not 1, okay, I call it 2 and 3. You have, this is x2 plus ix3.
So is there a way to write something similar for quaternions?
Yeah, because for quaternions you have, this becomes x2 plus ix3 plus jx4 plus kx5.
This is x. And what is
And then you have this x plus and x minus combined give you 0 and 1. So you have 0, 1, and you have 4 more, 6.
with pluses?
Well, they're just the
4 different combinations of that.
If you're in 4-dimensional space, you have 1 time and 3 space. You use the time and one of the space ones to do the diagonal elements, and then you're left with the other 2. And the other 2 you combine into a complex number. If you're in 6-dimensional space, you have 1 time and 5 space.
Yes.
You combine 1 time and 1 space to do the diagonal x plus x minus, they're real numbers. And whatever's left, you combine into the quaternion.
it's 2 real, it's 2, yeah, it's 2 real numbers, 1 here and none there, and then 1 number in this number system, right, which is 1, 2, 4, or 8.
The diagonal are clear, but do I need to pick some particular direction in order to have...
No.
The position is just the coefficient in front of I, J, K, and whatever. That's it.
So there are 4, like... there is x0, x1, x2, and x3.
x3 plus whatever,
Yeah.
how many more you get.
So what is the definition of x plus?
Well, x plus, you can think, don't even define. It's just a number. Call it x plus. You don't at this point. You don't even have to know that this is the case. Obviously, if I take the determinant, what I get here is just right. This here is just a product. This term here is just the product of. That's just x plus times x minus. And if you would recognize that as the Minkowski metric, I would have been happy just to leave it like that. But to put it in a form where everybody can immediately see that it's the Minkowski metric, I say let's call x plus and x minus x0 minus x plus minus x1. Okay.
So this example is specific.
And then the numbers come out. Why is it Lorentzian? Well, it just is. It just comes out, as you can see. That's a plus signature, and then the others are that's a plus, and the others are all minus. So it comes out as one time and the rest space. Pardon?
It's like light cone.
Yeah, that's right. Yeah, that's right. It's it's light cone. It's effectively like light cone coordinate. Well, it's light cone coordinates. It is light cone coordinates, in fact. That's one way of introducing light cone coordinates. So these are the transverse ones for a light cone. But the point is the transverse can be then in this number system as 1, 2, 4, or 8. Yeah? Sorry, what?
Oh, I see. Okay, yeah.
I'm not sure what the question was, but anyway, since it's answered, yes. Okay.
But the question, of course, is can you switch the order of L, or is there still the rule that the determinant of the product is the product of the determinant?
The answer is yes, but I'm not going to go into that. And even more so for the octonions, of course. And in fact, I should just make a point here that what's the number? You could say, well, okay, basically what I'm saying now is that you can see that essentially I can summarize it by saying that what I'm saying is that the Lorentz group is the same as this group in those particular dimensions, and you can just check that by, or you can, there's a check you can do, which is just to count the dimension of the group. Now you can see that that's 2 by 2 matrices of what I was just saying. There's 4 times dimension of k minus 1. If you count that for the octonions, it doesn't work. You only get 31, whereas you're supposed to get for the Lorentz group of 10 dimensions, SO19, it should be 45. In fact, the counting will give you 31. But there's a rule, which is that you add 14. I call it, but of course the guys who did don't call it that. They, 14 is the dimension of the automorphism of the octonions. It's with the group G2, exceptional group G2. You add 14, and part of the reason you can see that there's an issue, because if you imagine taking, and it's to do with the fact that it's not associative. You see, if you imagine acting with if you imagine trying to sort of group the group and you've linearized, and then you're acting on some space with one octonion, right? And then you come and you hit that with a second octonion, and then you do it in the other order. Now usually you get the commutator if you do that. If you take the difference between them, you get the commutator. Not for the octonions, because remember, you first of all used an octonion to hit something, and then you come with another octonion. Now you have to reassociate, so it involves the associator, which is non-zero. And so, it's subtle, very subtle. I just refer to the, I'm not going to explain, I don't understand the details, so I certainly won't be able to explain them, except that I can summarize it for you. It's an add 14 rule, and it always works. But look at the maths papers too. That's all I can say at this point. So now let me just say, so spinors are going to come into the game now. So let me just say that, so I've been talking about Lorentz vectors. Now what about Lorentz spinors? Well, Lorentz spinor is basically now, is just now a vector in K2. So in other words, A, B, where both A and B are in this Wheels complex, quaternions or octonions. And what is a spinor, first of all? Well, I've told you what it is here, so I could just take that as the definition. But of course, the point is that the Lorentz group, right, that is SO1D minus 1. And the point is that there's another group, the spin group, which essentially is the same, but there are elements in it which you identify in order to get this group here. And what that means is that you could have something in here which differs in here, but it will be the same. Sorry, the other. Yeah. So the I'm just getting the right way up. So the basic point is the representations. If you look at the representations of this, they're just vectors or tensors. But the point is you have additional representations of here, which are the spinors. You go around 360 degrees. You don't get back to the same thing. You have to go around again. But of course, if you identify those two, then you get back to here. I have only the vectors and the tensors. So anyway, the point is that you get different additional representations of this spin group, which are just the spinors. And the usual way you go about finding them is, so they're basically two valued representations of SO1D minus 1. And the usual way you go about finding them is that these are what Dirac matrices act on. So you have some sort of matrices of Dirac, and they have to satisfy the anti-commutation relations. That's 2 e to mn. And so this is some kind of matrix, and the vector on which those matrices are acting, they are the spinors. And then you can work out what dimensions they are, because you work out the minimal representation of this Clifford algebra, etc. So in 4 dimensions, you have 4 components. So, but the point is that you can, so in 4 dimensions, so let's take the case of 4 dimensions. So in 4 dimensions, in fact, as you know, the Dirac matrices are 4 by 4 matrices. In fact, you can take them to be real. So you could have the minimal one would be 4 real components. But 4 real components would be the same as 2 complex components. And that's the picture here, viewing them as SL2C vectors. Because then you just do vectors A and B, just both complex numbers, and they're simply acted on by this SL2C, it would be in that case. But the point is that generalizes to all of the other cases. So what we now have is so we now have the following. Yep. Well, I mean, there's the fundamental representations, and not necessarily the smallest, but for spinors. I mean, yes, the minimal one. You have in 4 dimensions, the minimal one has 4 real components, which could be a Majorana spinor, or you can represent as a chiral, as a 2-component complex. Vile spinor, exactly. So, but the point is you have a similar kind of dichotomy, as it were, in the other dimensions. So essentially what we have now is that in 3 dimensions you have spin 1, 2. That's the same as SL2R. And in 4 dimensions, you have spin 1, 3, and that's the same as SL2C. Of course, that gives you all the two-component spinor notation that you find in Penrose and Rindler. Or van der Verden, I guess, did it first, presumably over here in the Netherlands. And then you get spin 1, 5, and that's SL2H, and then you get D equals 10, which is spin 1, 9, and that's equal to, in this way that you have to be careful how you define it, this SL2O. So that's the situation, and what I now want to explain is the connection to supersymmetry. So that'll bring in this point about supersymmetry. Now, I'm just going to basically say a few facts. The simplest, in the case of, so Kugo and I had this table here, but we kind of supported it with sort of various empirical evidence. But the best evidence, actually, the best way of looking at it, in fact, came later by looking at super Yang-Mills theories. And so what happens if you look at minimal super Yang-Mills theories in D dimensions? So what you have is you have a vector. The point is you have a vector field and you have some spinor field. So M here is 0, 1 to D minus 1. And so this is anti-commuting. Anti-commuting, but the point is that alpha here is some spinor index. They call it running from, say, 1 to 2n, I think I've called it here. So 1 to 2n. At least if I think of them in terms of all real, total number of real components, let's say, is 2n. But you see, what supersymmetry always requires is equal numbers of bosons and fermions. So actually what that means is that you don't just count components here, you actually have to count polarization states. So the polarization states here will always be D minus 2. So in 4 dimensions you have 2 polarization states. So, so supersymmetry will tell you that D minus 2 will then have to be equal to, what are the number of polarization states there? Well, these are Dirac spinors, so, but you can take them to be minimal ones. So you then, but you have to divide by 2 because the spinor has a first order equation, so half of them are conjugate momenta, so you should only count half of them. That's one way of doing it, but if you just look at the field equations, you see that half are determinants of the other half. So it's actually n. So you can see that that's not going to be supersymmetric unless there's a relationship between this and this. And on the other hand, this tells you by you can just then go through the possibilities, because in each dimension you can work out what the dimension of the spinor is. But well, in fact, you can see it in those particular dimensions from here, what I was telling you before. But you can, in any case, work out it's 2 to the d over 2, and then you have to reduce by, if it's real, if it's chiral, etc. It's all a little bit dimension dependent, so difficult to write out in one equation. But nevertheless, this tells you, just by inspection of all of the possibilities, this tells you that D has to be equal to 3, 4, 6, and 10. So there we know that the super Yang-Mills theory, in fact, is you only have it in dimensions 3, 4, 6, and 10. Let me so that's also true for the Green-Schwarz superstring, which means, in other words, you can write it down only in those dimensions. Now, I've told you that would be followed just from supersymmetry, but actually that just follows actually from a free field. I didn't even have to do Yang-Mills here. It could have just been a free field. If you ask what about the interactions, then you discover that so I can use this one here. Well, I said super Yang-Mills theory, but you have a coupling constant. Put the coupling constant to 0, for example. Abelian, yeah, Maxwell. Then it's still true that supersymmetry would in fact tell you that this is 3, 4, 6, and 10. But then you could worry that, well, if I put the interactions in, am I going to be able to do it? It's up here. And the answer is yes, you can do it, again, precisely in 3, 4, 6, and 10 dimensions. But now, the reason that you can do it is because of an identity satisfied by the Dirac matrices. So, so if you the Yang-Mills interactions, they're consistent with supersymmetry if and only if gamma m satisfy. Okay, now I could write down what it is, but the trouble is it slightly differs according to the dimension you're in. And so let me just say it satisfies a Dirac matrix identity. I'm not even going to say anything more about it, but the point is, from that identity alone, then you do the analysis, you discover that this tells you again that D is equal to 3, 4, 6, and 10. So that's all good. It just confirms what you already knew. But now there's an interesting point about this, which I don't have time to explain in much detail, in any detail, in fact. The point is that just the gamma matrices themselves in these dimensions have the effect that they turn the space of vectors or spinors into a normed division algebra. So this also implies, so this was, I mentioned there was a paper in 1987 by my colleague in Cambridge, Jonathan Evans, who in fact relied on mathematical work by Adams previously to do with trialities and so on, which I won't go into. But the point is that this also defines a normed division algebra. So if this is in D dimensions, then you can conclude that there exists, if Yang-Mills theory exists, which implies this identity here, then there exists a normed division algebra in dimension D minus 2. But we know from the Hurwitz's theorem that in fact D minus 2 then has to be 1, 2, 4, 8. So we're back to this thing here. And now there's a direct relationship. So the existence of the division algebras is directly related both to the existence of supersymmetric Yang-Mills theories and the Green-Schwarz superstring, which is remarkable. Okay, there are other things that one could say about supersymmetry, but I think at this point I'd prefer to move on. So there's a connection here with the division algebras, a definite and concrete connection between the division algebras and supersymmetry. So what I'd like to do now is to get the twistors into the game. How does that come in? Okay, so what I'm now going to look at is just particle mechanics, and in particular, massless particles. So
but this was for D minus 2 in condition representation, and here making division algebra are kind of independent, right? But they kind of coincide. Is this a coincidence? Is it?
No, I'm saying I'm saying that you can independently show that there's an identity satisfied by Dirac matrices.
Yes.
It's to do with properties of Clifford algebras, right? And then you say, and you show that this particular identity implies so if you know that this identity is true in D space-time dimensions, then you know, according by this theorem, that there is a normed division algebra in dimension D minus 2.
Yeah, I mean,
right.
This fact about D minus 2 and another fact, right? The previous one you wrote about the commission matrices representation, right?
Yeah.
Is this coincidence? Is it coincidence? Is it investigated?
No, it's not a coincidence, of course, but yeah. I mean, it's kind of implicit. If you remember how it was written, I mean, you had an x and an x bar, and so you get the norm by taking x and x bar.
Okay, so
and it's it all relies on the fact you have conjugation and so on. It relies on the fact that essentially you have one of these, one of the 4 division algebras. If you didn't, you wouldn't get anything that looks nice. But you're right. I didn't. I didn't prove all of the steps and. I showed that you could do it. I didn't say you couldn't do it if you didn't prove to you couldn't do it if you weren't in those dimensions. But I'm pretty sure you can't. Yeah. So the point now. Let's look at massless particles. Massless particle. So the point is again, we can have PM. So take the momentum. So I had X previously. Write that as some 2 by 2 matrix P. Now this will be P0 plus P1. Right, P0 minus P1, and I have P bar. Where now P is an element in that division algebra. Now the point is that the mass shell constraint is P squared is equal to 0. But that's equivalent to saying that the determinant of P is equal to 0. And that can be solved. I'll call it a spinner. It's a spinner, but it's really a vector of this SL2K. The point is, and I call it a U. So let's introduce a U. And the point is, it's simply the statement that, so for example, in D equals 3, it's simply the statement that in order to have a non-degenerate, you can always write a matrix as in terms of some vectors. Just take the tensor product of vectors. So you take one vector if you take its tensor product, but the problem is it's a 2 by 2 matrix. So in order to have a non-degenerate 2 by 2 matrix, you're going to have 2 vectors. If you only take one, then immediately the determinant is equal to 0. So for example, if I take D equals 3, you see what happens here. This is just a symmetric matrix then. So in D equals 3, you would have P alpha beta, right, is equal to, and I'm saying that I'm going to write that as U alpha, U beta. Where U alpha and U beta are just 2 component reals. But immediately that's the determinant is equal to 0. So that solves the mass shell constraint. And now what we can do, and the statement is that, well, you see, it's not actually immediately obvious that that's going to work if you have K's, you start doing the quaternions and the octonions. But in fact, this statement here, this statement, you can solve it in this way, is actually equivalent again to this direct matrix identity. So although, if you work on it, you see that actually what you're using is this. But at least in these simple cases here, at least in the 3-dimensional cases, you can see it immediately what's going on.
If I'm doing it in if I'm doing it in in say complex or something,
yeah.
like that, be UA, U bar, B or something.
Well, it would then be P alpha P beta dot, because you have the chiral and anti-chiral spinners, and then this will be U alpha U bar beta dot there. And then the same thing would apply, and it's. But I do it in 3 dimensions because first of all that's the simplest, and also what I want to do is just look at the 3-dimensional case here. You see, the point is if you now look at this quantity here, XMPM, okay, I could have written this in 2 by 2 matrices, and it would have been the trace of X dot P. But, I should say this is, let me see, I'm going to go back to vector. See, this is actually equivalent to saying that, it's equivalent to saying that PM is equal to 1/2 U bar gamma M U. So U bar is actually the Dirac conjugate, so that's basically U transpose. So U bar is U transpose times the charge conjugation matrix, which you can take to be gamma 0. Yeah, so for those who don't know, but so that's an equivalent way of writing that, in fact. And by the way, the Dirac matrix identity here is basically the DMI in this case is essentially, it says that P slash U is identically equal to 0. So that's what it is in this case. So if I make this substitution, you can easily see what happens in here. I'll integrate by parts. So I'll throw the time derivative across oh, actually, excuse me, I should have said was going to say something first, because before discussing this, because I just wanted to say a few words about particle mechanics. So, in fact, let me just, if I have time to do that, so let me just park that calculation for a moment over here. Let's just, I'll start this again in a moment. But, so let me just park this for a little while I just make a few points. Yeah, so as I said, what I want to do is to look at these things in the context of the mechanics of a free particle. So first of all, but it's useful to have that in a particular form, which is, it's useful to have it in a form which is reparameterization invariant. So let's just have a look what that is. Reparameterization invariant particle mechanics. So the point here is that supposing you're given a Hamiltonian H, say you have, this could be, for example, non-relativistic. XP could be a function of x0, so non-relative. Let's take non-relativistic. Given a non-relativistic particle Hamiltonian. So it depends on the three position, 3 momentum in 3 space dimensions, and on the time, which I'm calling x0 here, in principle. Then the point is that you get, so in that case, Hamilton's equations follow from the action where you take S is equal to dx0, and you then just take x dot p minus h. That's the standard thing. But what I'm now going to do is just to rewrite that as I'm just going to rewrite that in the following way. The point is that we want to consider this. So we now consider variables as functions of arbitrary parameter. Call it t. And then you can write the action in the following way. S is equal to, then we're integrating over this parameter. And we have the term we had before, some new term here, and then I have a Lagrange multiplier for a constraint. And well, you can see that the point is that why is this the same? Well, the point is now it's invariant on the reparameterization, so you can always choose. So equivalence, to prove equivalence, you simply choose x0t to be equal to t. Then, of course, that will become dx0. This term becomes minus p0. But then this tells you can solve this constraint, p0 is h. And then solve constraint. This gives you that p0 is equal to h. And then, of course, we're immediately back there. So that's a completely equivalent way of doing it. But notice that I can simply rewrite that now as, let's call this, I can rewrite this term here as just xm dot pm. I push the 0 down and call the 0 that with a minus sign. That would be plus, and so that's this. And this now depends on x0, xp, and the x0. So it's just some function here depending on all of the x's and all of the p's. And so you have, now we have basically that that s is equal to dt x dot m pm minus e of t h, for h takes this particular form, and that's the action for a non-relativistic particle. And if you want to go for the relativistic particle, you simply say for the relativistic particle, you just take a different function here. And in fact, you take h is equal to 1/2 p squared plus m squared. And then you get the relativistic particle. Because obviously, if you solve for p0, you get the square root of p vector squared plus m squared for the Hamiltonian. Now, what I want to do is, in fact, to take the massless case here. So, for the massless particle, I have so for the massless one, I get s. I get s is equal to x dot m pm minus e p squared. And so the point now is that what I'm going to do, I was telling you for a massless particle, you see you can solve this constraint in this way. And let's just take the case of d equals 3. And if you substitute, then x dot m pm, you see, goes to, I'll do it in this notation here with this u bar gamma m u. You see that let's integrate by parts, throw the derivative across. Let's decide we're going to hit this one here. That's a factor of 2. So that's equal to u bar dot, and then I have x slash u plus d by dt of something which won't matter. And let's call this quantity here w. So now what we end up with is that an action which is dt u bar dot w. That's it. Now, what's interesting about that? Well, in some sense, nothing, because it's just about the simplest thing you could write down. It's obviously completely trivial, because the equations of motion, right, is that u bar dot is equal to u, is basically u dot is w dot is equal to 0. So it's just a point on this space. So the solutions are points in the space, basically uw. Now, what is this space? So we reduced solving the equations of motion, which admittedly was pretty trivial, wasn't it? It was just a null line. But now we've reduced it to just finding a point in this space. But if you ask, well, what is that space? You see, have a look at the other point about that action. It looks pretty completely trivial here, u bar dot w. You see, that has 2 components. That's another 2 components. That's 4 components. You see, it's a kind of pq dot. It's actually, it's just determined some kind of some set of Poisson brackets, or equivalently a symplectic form. In fact, what this is invariant under is canonical transformations, because the canonical transformations preserve Poisson brackets. So this is invariant under any canonical transformation you care to mention. And the canonical transformations, they preserve some antisymmetric tensor on this 4-dimensional space. Actually, that's infinite dimensional group. But if you look at linear transformations, essentially what's going on is this is invariant. So this is invariant under canonical transformations on R4. But that includes, as a special case, if you look at the linear ones, that includes, by definition actually, a group which is SP. SP is for symplectic. It basically means canonical transformation. 4 is because it's in 4 dimensions and they're real over the real. So it's actually this. And if you know how to work out the dimensions of that, you'll see that in fact that has another name. That's actually the same thing as, again, as the spin rather than the orthogonal group. A 2D, a 2, 3. But this is in fact the conformal group in D equals 3. And you see, it's exactly as I was saying before. What's a spinner of this orthogonal group, or spin group if you like? Well, you rewrite that in this way, and then it's just a vector of this. So it's really just a 4-component vector, which puts, it's this one here, u and w. So u and w is actually just a vector of this, which is a spinner of the conformal group, but that's called a twister. So this is a twister. So uw equals a spinner of the conformal group. And that's a twister. So that's what a twister is. And you can see some of the virtues, well, some of the things about twisters you can see from this simple 3-dimensional context, because you can see that what happens is that you see you exchange lines and points again. Because look what happens. I've just told you already, we've seen that your point, so we have this point, we have this observation that a point in this twistor space is a null line in Minkowski space. So a point in twistor space equals a null line in Minkowski. On the other hand, you can see from this relation here, you see from the relation that w is equal to x/u, if you pick x, that just defines a line in the twistor space. So a point in Minkowski space is, in fact, a line. Well, a particular kind of line, but anyway, it's a line in twistor space. So you have two kind of dual ways of thinking about it. And that's the simplest case of a particle in 3 dimensions. Now, twistors, of course, now the point is, you can imagine from what I've been saying, that the point is that you can do the same thing, not just in 3 dimensions, but you can do it in 4 dimensions, you can do it in 6 dimensions, you can do it in 10 dimensions. Although if you want to do it in 10 dimensions, I again refer you to the mathematics papers, because you have to add 14 again to get it to work. But I wanted to just say a few words more about the 4-dimensional case, if I have time, but I don't. No. Good. Okay. Okay. Then I should. I forget when I started exactly, but I should. Okay. Oh, I've gone over already. Okay. So sorry about that. Okay. I'll just stop here by saying that. So you can. So that's the point. You can extend it to all these other cases. And as I suspected, I didn't have time to say any of the other things about supersymmetry and how you can extend it to the massive case and get 11 dimensions into the picture, but okay. At least I hope you've been able to take something away. Yeah. I'll stop there.